Swayam Prabha. Digital India. Educated India.
So, welcome to Compaction of Soils part 6 lecture. So, in the previous class we have seen field compaction and specification and different methods for determining the field compaction, and we also reviewed different types of compaction equipment which are available for ensuring compaction in the field. In this lecture we will be introducing the in situ densification of some soils, predominantly granular soils, and then we will see two illustrations 1.1 and 1.2 which illustrate the problems pertaining to compaction. Particularly we will be seeing a problem and then we will be solving the problem in the form of a solution. So, in the previous class we have discussed that the importance of the lift which is available in the compaction process in the field. So, let us look how it is actually possible for us to select the lift thickness. So, if the lift thickness are too large, so as it shown here, if the lift thickness are too large, then the following will occur, in the sense soil at the top of the lift will be well compacted. That means that in this zone it will receive well compaction, and at the bottom of the lift will not be compacted at all. So, the lift thickness selection is a very important criteria in the field compaction. So, if the lift thickness is too large, only the top soil will be compacted and bottom soil will not will be able to satisfy the criteria. So, there is a certain criteria which is required to be followed to see that the minimum set specified compaction is achieved or not. Consider in this slide where at two different layers, if we specify as the 95% density as the required density for adequate compaction, then at the mid of the layer there will be the density gradient will be high, at the top and bottom it will be less. So, here if you see, if I set 95% gamma d, that means that this particular layers, two layers, if this lift thickness is adequate, then we say that both the layers have achieved the adequate compaction. In the case of this, if you see here, the set criteria is this much, 95% gamma d line is here, but most of the areas now here and here and here, which is falling less than this particular requirement, which shows actually the inadequate compaction. So, the lift thickness is very much important, and to satisfy the required compaction in the layer uniformly. There will be, for the most compaction equipment, lift thickness should typically be on the order of 150 to 200 mm. So, what will happen is that once the roller which is exerting energy, this is in the form of a pressure bulb, and what will happen is that the area which is very close to the roller is something called high stress region, and it gets well compacted, and below is low stress region. So, that is what it happens here. The wheel of the compaction equipment is shown here, and high stress region is here, it shows well compacted zone, and here is the low stress region indicating the layer is less compacted. So, if the layer thickness is large, then this actually spreads to the bottom most of the layers will not reach the required compaction. Now, if you look into this slide where it shows field density versus field dry density versus number of passes. In the previous lectures also we have discussed that the number of passes required for a wetter soil will not make much difference. So, in this slide if you see for a wetter soil, the dry density achieved is very much uniform with increasing number of passes. So, the increasing number of passes on the wetter soil is turns out to be futile, because it will not have any effect in increasing the dry density. Whereas, a drier soil or some natural soil has got this effect which is shown here. This is a figure which shown dry density versus number of passes for one layer thickness. Considering an increasing the layer thickness, for example, layer thickness increases, that is lift thickness increases from 150, 200 and 300. Suppose if the layer thickness is increasing, for a given number of passes you can see the dry density achieved will be less. For a layer with 300 mm lift, for a layer with 150 mm, for a same number of passes the dry density achieved will be high. So, this shows the correlation between dry density achieved and thickness of the lift in the field compaction process and number of passes. So, for any job it is required to be a trial and error procedure has to be arrived, and see that the correct number of passes are arrived for a given type of soil and for a given type of job, so that the adequate compaction or a set compaction can be achieved. So, here approximate method for determining the lift height required according to D. Apollonia 1969 is present here. Here in this case the relative density, basically this has been done for a granular soil, a relative density which is plotted for a layer thickness, a single layer thickness. This is the depth in meters, the thickness of the layer, and the density achieved. So, somewhere here the maximum density is achieved here with the single layer thickness. So, density depth relationship for large lift height using 5 roller passes, whereas the same layer compacted in number of layers, you can see this is the set density which is achieved. That is, suppose if I say that minimum allowable relative density is 75%. So, this particular thickness is qualifies as required minimum lift thickness for compacting the granular soil in the field. So, here what we have seen in this slide is we have tried to see the approximate method for determining lift thickness in the field. So, there we have seen something like each layer is compacted in different zones, and then the field compaction basically relative density has been assessed and plotted against the depth to see that whether it is above the minimum set specification or not. For example, in this case a minimum set 75% relative density is satisfied for a layer which is of 18 inches or so. So, let us look into some illustration pertaining to the compaction. So, problem number 1.1. So, in the given data in this case is water content versus dry unit weight data is given for a standard compaction test, and the specific gravity of the solid particles is given as 2.70. So, the standard Proctor compaction has been adopted, and this is the data which is given in the slide, which shows that water content versus gamma D, that is the dry unit weight in kilonewton per meter cube. So, the tabulation shows that these are the results which are obtained from the standard Proctor compaction test. What we are required to do is that plot 80% and 100% saturation lines. So, first of all we are required to plot compaction curve, and if it is proposed to secure a relative compaction of 95% in the field, that means that 95% of the maximum dry density which is achieved in the laboratory. In this case, once we plot, we will be able to determine gamma D max and optimum moisture content. And what is the range of water content that can be allowed? That is in part A. In part B it is asked here, and part C, would the 20% air voids curve be the same as 80% saturation curve. So, there is so it is a 3-part problem where we are required to solve in steps. So, let us try to look into the solution. So, we were given the data water content versus dry unit weight. So, first of all we have to plot water content on the x axis and dry unit weight on the y axis. So, having plotted, let us see if we plot water content on the x axis and dry unit weight on the y axis, and these are the different points which are given as a result of the compaction test, standard Proctor compaction test. So, with this now the maximum dry density at a optimum moisture content of around 15.17% is 17.45 kilonewton per meter cube. So, you can see here with increase in water content there is a maximum dry density or dry unit weight has been reached, and then at a particular or unique water content for that particular type of soil, where the optimum moisture content in this case is around 15.17%, and then with an increase in water content beyond the optimum you can see the decrease in the dry unit weight. Now, using gamma D is equal to Gs gamma W by 1 plus Wgs by Sr, draw this 100% saturation line and 80% saturation line. So, 100% saturation line can be obtained by putting Sr is equal to 100 or is equal to 1 in the equation which is shown, gamma D is equal to Gs gamma W divided by 1 plus Wgs by Sr. Gs is known to us. Similarly, by putting Sr is equal to 80%, draw 80% saturation line. So, as you can see here, this is the 100% saturation line, which is also called zero air voids line, which is on the right hand side of the compaction curve. So, at optimum moisture content and maximum dry unit weight, approximate dry unit weight is around 80% or so. So, having determined gamma D max and optimum moisture content, now we have solved part A, and we also solved something like called 100% saturation line and 80% saturation line we have plotted. Now, we have to we are required to further examine these results to obtain the results in the field. Now, it is given to us that relative compaction is proposed to achieve around 95% of the maximum dry density obtained in the field. So, we have obtained maximum dry density in the laboratory around 17.45 kilonewton per meter cube. So, gamma D field can be obtained as 0.95 times 17.45, which is around 16.58 kilonewton per meter cube. So, if you look into this curve, the previous plot curve, if you see here, the range of for a 16.58 kilonewton per meter cube, which is the field dry density which is possible in the field. So, for that dry density, if you look, the range of water contents ranges from somewhere around 10 to around 15 to somewhere around 17 to 18%. So, exact figures can be around 10 to 17%. So, we have a flexibility to achieve this 16.58 kilonewton per meter cube. We have water content to be maintained in the range of 10 to 17% in the field. Now, further it has been asked whether this 20% air voids curve is same as this 80% saturation line. Naturally, the definition from the fundamental definition, air content is equal to 1 minus SR, that is SR is nothing but the degree of saturation. Na is percentage air voids is N times, that is porosity times AC, AC is nothing but 1 minus SR. So, Na is equal to N into 1 minus SR. So, using the data, if you adopt, then we will be able to justify that the 20% air voids curve is not the same as the saturation line, 80% saturation line. So, here by using this approach also, we can prove that using gamma D is equal to Gs gamma W into 1 minus Na plus 1 plus Wgs. This you may recall, this we have derived in previous lectures. So, for given water content, say W is equal to 8.5%, that is the starting water content in the data given to us. Na is percentage air voids, that is it was given to us 20% air voids curve, that is Na is equal to 0.2, and gamma D is 17.22 kilonewton per meter cube. So, with this data, by using this, we will get gamma D is equal to 17.22 kilonewton per meter cube, which is different from 20.56 kilonewton per meter cube for degree of saturation of 80%. So, this is for 80% saturation line. If you calculate, what you will get for a water content of 8.5%, the density or unit weight is around the dry unit weight is around 20.56 kilonewton per meter cube, which is different from this. So, with this also we will be able to say that the 20 air voids curve is not the same as the 80% saturation line. But we can also say 80% saturation line is same as 20% air content line, because AC is nothing but, air content is nothing but 1 minus SR. SR is degree of saturation. Now, let us look into the illustration compaction 1.2. We were asked to determine the values of dry density at selected water content values for Na is equal to 0, 5 and 10%, assuming the specific gravity of the solids Gs is equal to 2.67. So, we were asked, the problem statement is as follows. Part A, it is in 4 parts, and part A, determine the values of dry density at selected water content values ranging from Na is equal to 0, 5% and 10%, and assuming that the specific gravity of solids as 2.67. Now, again using gamma D dry unit weight is equal to a relationship for a partially saturated soil, Gs gamma W into 1 minus Na by 1 plus Wgs. For Na is equal to 0, 5 and 10%, determine the values of gamma D for selected range of values of water content. And using the compaction data for standard product compaction, plot the results again on the dry unit weight versus water content. If you do that, then we will be able to get this relation like dry density. In this, dry density is defined here as with the units mg per meter cube, and moisture content or water content indicated in percentage. So, this is the laboratory result which is plotted here, and these are the from the given the data we have generated 0%, 5% and 10% air void lines. These are the air void lines, that is Na air void lines, and you can see here this is the maximum dry unit weight, that is maximum dry unit weight is around 1.902 and optimum moisture content is around 11.9%. So, this 11.9% is the optimum moisture content, and maximum dry unit weight or dry density is around 1.902 mg per meter cube. So, what we have to see is that what are the, for example, if I say that I specify a 5% air void lines, then with that as criteria I will be able to decide what is the range of water contents I have to allow in the field. So, that is actually very much required to control the soil moisture in the field during compaction. So, having set in part A, now let us look into the problem statement in part B. In the part B, determine the void ratio, degree of saturation and percentage air voids Na at optimum moisture content. So, previous discussion we have determined maximum dry unit weight and optimum moisture content. So, we said that optimum moisture content is around 11.9% and rho d max, the dry density, is around 1.902 mg per meter cube. Now, rho bulk can be determined as rho d max into 1 plus W or moisture content is nothing but 2.128 mg per meter cube. So, using rho bulk is equal to Gs into 1 plus W rho W divided by 1 plus E, with that substitutions we will be able to determine what is the void ratio. So, void ratio in this case works out to be around 0.41. So, having known void ratio, by relation between void ratio and porosity, we can determine the porosity of the soil. The porosity of soil in this case is around 29%. Then by knowing E is equal to Wgs by Sr, the relationship between void ratio, water content and specific gravity of solids and degree of saturation, we can determine degree of saturation, and that works out to be around 79%, 78.7%, which is approximately 79%. So, now the percentage air voids which are there at optimum moisture content, that is our interest in we are required to determine. So, we were asked to determine percentage air voids Na at optimum moisture content. So, we have determined the porosity and we have determined degree of saturation. So, with that we will able to say percentage air voids is equal to N times Ac or N into 1 minus Sr. So, having known SR, having known porosity, now we will be able to determine percentage air voids Na as 6.1%. So, the percentage air voids at optimum moisture content, even at optimum moisture content, the percentage air voids which are remained there are around 6.1%. Coming to part C of this illustration compaction 1.2, here now we are trying to relate to the field compaction. The minimum dry density to be achieved in the field by field compaction has been specified as 95% of the Proctor density. 95% of the Proctor density was given. Determine the minimum moisture content which must be specified to ensure that no more than 10% voids may be present. No more than, so 10% voids are to be allowed, and determine the maximum value of moisture content W that can be permitted. So, field dry density, which is now we can estimate as 0.95 times the maximum dry density in the laboratory, which is 1.902, we have determined from the previous deliberation. So, the field dry density is now around 1.807 mg per meter cube. So, using rho d is equal to Gs rho W into 1 minus Na plus 1 plus Wgs, we can determine W is equal to 12.3%, that is the minimum water content. That is Na is equal to, here is given as 10% to us. Note that this minimum moisture content would only apply if the field compaction energy is less than the laboratory compaction energy. So, this minimum moisture content will only apply if the field compaction energy is less than the laboratory compaction energy. So, here if you look into it, the maximum water content that can be obtained assuming that the wet of the compaction curve achieves with 5% air voids. So, repeat the same process by for 5% air voids, if you determine the water content works out to be around 15.1%. So, if you look into this here in the field for the desired dry density of around 1.807 mg per meter cube, I have a flexibility to vary the water content between 12.3% to 15.1% as per this problem statement. So, it says that the soil in this zone, the soil or this particular thing is accepted, meets the specifications. So, this is actually how we decide that it meets the specification or not. So, this is about the illustrations problems 1.1 and 1.2. So, what we try to do is that from the laboratory data, and we are setting the specifications and trying to see what are the range of water contents we will be able to allow in the field, that actually we are trying to estimate and understand. So, having seen, now let us look into another type of compaction method is called impact compaction. The impact compaction, it is the transfer of the compactive energy into the soil by means of lifting and falling motion of non-circular rotating mass. So, the impact compaction is nothing but the transfer of compactive energy into the soil by means of lifting and falling motion of a non-circular rotating mass. It is thus a process capable of transferring impact loads similar to those found in dynamic compaction on a continuous basis. So, here in this impact compaction, the object something like called non-circular object will be able to induce energy to the soil, something very similar to the dynamic compaction. So, the depth of the extent of the compaction will be very high. So, this impact compaction is also another type of compaction method which we have not covered in previous lectures. Now, we are trying to see what type of impact compactors are available and how this depth of compaction is comparable with the other static compaction and vibrability compaction, etc. So, this is a typical impact compactor. So, this is what actually the impactor which was described earlier as a non-circular impact. So, when this rotates, it creates a wave type of energy and tries to compact the soil to the greater extent. The features of impact compaction, if you look into it, we have the higher energy is possible. Higher energy in the sense the energy rating of the different impact compaction equipments range from 10 kilojoules to 25 kilojoules. Higher energy helps to achieve higher maximum dry density that allows to work over a wide range of moisture content. Just now we have seen that the range of moisture contents we have followed. So, to achieve that higher densities, this type of process may allow us to achieve those densities in the range of the moisture contents which are possible or which are possible to maintain. So, higher energy helps to achieve the higher maximum dry density that allows to work over a wide range of moisture contents. So, here in this slide it is shown the dry density versus moisture content. Suppose this is the conventional compaction, if I get a curve like this for the range of water contents, and this is the 0 air voids line, then here this is due to the impact compaction. So, that in the range of given water contents we will be able to achieve higher dry densities because of this particular type of impact type with the energy which is produced because of the non-circular type of object. The features of impact compaction, if you list them, increased depth of influence, that is one attribute is the increased depth of influence, with one of the attributes is the increased depth of influence. So, let us see the contact stresses of impact compactor varies from 300 kilopascals to 1200 kilopascals, exceeding conventional roller and depending upon the soil stiffness. It also depends upon the soil stiffness. The contact stresses, they range from 300 kilopascals to 1200 kilopascals. Impact roller's profile radius is not referenced to the center of the drum, greatly exceeding the conventional rollers, resulting in a greater contact area. So, this is not being a circular roller, it is possessed to have greater contact area. So, the greater contact area the field soil is possible with this. So, impact roller's profile radius is not referenced to the center of the drum, greatly exceeding the conventional rollers, resulting in a greater contact area. That is what actually has been discussed in the second point here. The net result is the superior depth of influence, enabling compaction layer thickness exceeding 1 meter. So, with this sometimes even the large lifts like 1 meter also can be compacted efficiently with higher dry densities. So, in the slide here, a typical static roller and a typical vibrating roller and a impact roller has been compared. So, let us see the depth of influence for a static pressure and kneading type compaction. You can see that D1 is the depth, and vibratory energy of lower amplitude and high frequency, you can see D2 is the depth, where D2 is greater than D1 for a vibratory energy of low amplitude and high frequency. You can see this is the H2 is the vibrating this thing which is produced about its vertical axis, and because of the impact compactor impact energy of high amplitude and low frequency, the depth of the influence is D3. So, overall the D3 which is greater than D2 and D1. So, you can actually this slide can illustrate us the superior depth of influence of or spreading of the compaction energy because of the impact compactor. So, here the drop height, if you see here, which is H3 greater than H2 and H1. Here the drop height is very less, almost less, and here this H2 is less than the drop height which is H3 here. And the features of the we are now covering the features of impact compaction. Increased load duration. The impact compactor's load duration has been measured to be approximately 10 to 15 times longer than that of the conventional rollers, and this allows for a softer soil response and its enhanced compressibility is attainable. So, the impact compactor's load duration has been measured to be approximately 10 to 15 times the longer than that of the conventional rollers. So, that is one of the important features which is available with the impact compactors. So, here the increased load duration, the soil response versus load duration is shown. So, this is with when the soil response is for typically 0.02 seconds duration, the soil response is very high here, but you can see here with typically the 0.12 seconds, the longer duration results in reduced soil response and greater compaction. So, the soil response, that means that opposing the energy which is supplied because of this compaction is less with the longer duration. So, here the impact compaction able to produce the longer duration, so that a greater compaction can be achieved. Another feature of the impact compaction is the high operating speeds. Land pack impact compactors is the type of the compactors which are used generally in the field, operate at speeds up to 5 times faster and 10 times greater volume per day than the conventional compaction equipment. So, we are trying to compare with the conventional equipment. So, it says that 5 times faster and 10 times the greater volume. So, because larger lifts can be compacted, so the volumes of the compaction will be high. So, having seen some problems that is and the solutions for how to control moisture content in the field, now let us try to see what are the different methods available for in situ densification of certain type of soils. So, many times the man-made structures are constructed on the existing soil deposits. Sometimes these soil deposits are required to be densified before constructing a structure. So, for such type, in order to reach or attain compaction up to deeper depths, then in situ compaction methods have to be adopted, because the roller compaction, all these things will not be affected, will be effective only up to certain depth of influence. So, for that to happen, there are certain type of methods. Let us look into these different type of methods which are available for in situ densification of soils. So, in this slide, there are several new techniques such as terraprobe method, vibro flotation, building sand compaction piles, blasting and dynamic compaction. So, mostly for loose sandy soils, one of the alternative is to place and replace some of the loose soil with a column of soil having high density, high relative density. So, that is called a column of soil which is replaced with high relative density is called a sand compaction pile. So, that is one method which can increase the overall load carrying capacity of a soil deposit. The other one is vibro flotation, which is an in situ technique, and this is also an in situ technique, and a blasting or by explosives or by dynamic compaction or compaction by pounding, basically releasing of the repeated heavy blows onto the soil deposits. So, these methods have been successfully used for compaction in situ soils, especially for granular soils and sandy soils. So, these are the different methods. Now, let us look into some of the typical methods like vibro flotation, blasting and dynamic compaction. So, this is a terraprobe method, and here it shows it has got a vibro driver sitting on the probe. So, this works best for the shallow water table. Suppose if the water table is at shallow levels, that is up to 2 to 3 meters below the ground surface, then this method will be very effective. And this method requires densification at spacings ranging from 1.5 to 2 meters. You can see that S is equal to 1.5 meter is the general this thing. So, activated vibro driver causes the probe to vibrate in the vertical direction. So, this is the vibro driver which is shown, and this is the probe. So, when this vibro driver is nothing but the one which is used for pile driving equipment. A similar one, what it does is that it induces the vertical vibrations in this direction, so that when the probe, because of the presence of the water table, that is for the shallow water table, this can penetrate into the ground and densifies the soil. To achieve soil compaction, the probe is vibrated to the planned depth of penetration. So, this is a terraprobe method which is shown here. This is a rig which is holding the vibro driver along with the probe, and this is a slide which shows a picture of the vibro driver sitting on the probe. So, the next method which has been mentioned is vibro flotation. So, this is a method which is widely used for in situ densification of granular soils. So, with this method, deeper depths of soils can be compacted to a reasonable degree of high relative densities. When conventional rolling type compaction equipment walks the surface of an area, the improvement in the density is limited to the surfacial zone of the deposit. Typically, depths below a meter or 2 experience a little or no increase in density. So, we have discussed also that if a conventional compaction equipment is used on a loose sand deposit, then or a gravel deposit, the energy which can be imparted to compact the soil may reach only up to a meter or 2 meters depth. So, in order to compact the soils into even at the deeper depths, then we have to resort to a method which is called as a vibro flotation method. So, vibro flotation equipment operates from sites at a ground surface, but it can densify the full depth of the granular deposits which are as deep as about 12 meters. So, vibro flotation, this particular technique has got a device called vibro float, and which is used in the field very widely, and up to as depth as around 12 meters the compaction can be achieved with this particular type of method. So, this vibro flotation method, the range of particle size distribution suitable for densification by vibro flotation, because before selecting any method we have to look into what are the type of soils to which this method can be applied. For example, this particular slide which shows a particle size percentage finer versus particle size for the range of soils, and this soil this chart is applicable for compaction by explosive, compaction by pounding, as well as for vibro flotation technique. So, here you can see that this is the most desirable range which is shown here with this rhombus type hatching. So, this is after Mitchell 1970. You can see that mostly the gravel sand deposits and partly some silty soils and very less clayey soils. So, this is basically for gravel, sand, and predominantly to some extent silty soils can be used. So, we can use this particular vibro flotation method for gravelly, sandy soils and particularly to some silty soils, but very less for clay soils. So, vibro flotation, it involves the process involves the use of a device called a vibro float. The device is called vibro float, and which is a cylindrical piece of equipment about 2 meters long and 400 mm in diameter, weighing about 17.8 kilonewtons, around 1.78 tons. So, the vibro flotation involves the use of a device called vibro float, which is in a cylindrical equipment, is 2 meter long and 400 mm diameter, and having a weight approximately 1.78 tons. The eccentric weight inside the cylinder develops a centrifugal force of about 89 kilonewton at 1800 rpm. So, the eccentric weight inside the cylinder develops a centrifugal force of about 89 kilonewton at 1800 rpm. The device has water jets. So, this device has got water jets all around the periphery or at the bottom, and with that it able to induce and progress in the in penetrating into the soil. So, the device has water jets at the top and bottom, and these have a flow rate of around 0.23 to 0.3 meter cube per minute at a pressure of around 415 to 550 kg per meter square. So, the device has water jets both along the sides as at the bottom to allow it to penetrate into the ground and to reach at the desired depth of penetration. So, the flow rate which is set around 0.23 to 0.3 meter cube per minute with a pressure at a pressure of around 415 to 500 kilonewton per meter square. And the vibro float sinks into the ground at the rate of around 1 to 2 meters per minute. So, around 1 to 2 meters per minute it tries to sink into the ground, that is the rate at which that means that per minute it can sink by 1 to 2 meters. When the desired depth is reached, the top jet is turned off. When the desired depth is reached, the top jet is turned off. The device is then withdrawn at the rate of around 0.3 meter per minute, and the sand is added from the top. So, in a regular working day, a compaction of about 2500 to 5200 kilometer cube is not uncommon. So, generally in a regular working day, about 2500 to 5200 meter cube of soil can be compacted. So, this process involves we are going to see the sequential steps in the subsequent slides, where the vibro float is a device which is allowed to penetrate into the ground and create a desired compaction at the deeper depths. Now, here this vibro flotation scheme is shown here, where we are seeing the vibrator which is penetrating into the desired depth, and this is the rig which is holding the vibrator, and these are the typical granular soils which are undergoing compaction. and here this is how the water is spreading and creating a densification surrounding the areas, and here this is the compacted soil with the release of the sand from the top. So, this process what will happen is that while retrieving this, the sand will be sent into that. With that the process this soil gets compacted. In the process what happens is that the soil within the vicinity of that particular probe will gets compacted. So, like this it is required to cover the entire area at optimum spacing, so that the net soil deposit which is there is approached to have high bearing capacity or high load carrying capacity for the desired structure to be coming on to that soil deposit. So, this is the process which is described here in this slide, where in this slide what we are seeing is this is the vibroflow device, and this is the bottom jet which is open now. At start the lower jet is opened fully. So, what it does is that when it penetrates into the ground, because it has to create something called a quicksand condition, where momentarily the soil loses the strength. So, for that before the rate of flow of water is more than the water draining rate. So, if I am able to do that, then momentarily a quicksand condition can be achieved. So, water is introduced more rapidly than it can drain away. That is the thing which is followed here, and this creates momentarily quick condition ahead of the equipment, which permits the vibrating machine to settle of its own weight to the desired depth. So, with its own weight it is able to penetrate into the ground. So, in the process what is happening is it is momentarily creating something called a quicksand condition, where the soil is giving way for the vibroflow to penetrate into the soil and its own self weight. So, in this slide you can see how the soil is the jet is pushing and the soil is the progressive penetration of the vibrofloat. When here you can see in this slide, with this now the sand is being added. So, the water from the lower jet is transferred to the top jets now, the top jets are also there, and the pressure and the volume are reduced just enough to carry the sand to the bottom of the hole. So, once the sand supply is started, the bottom is switched off and the water is now opened from the top and sides here you can see. So, the water from the lower jet is transferred to the top jets and the pressure and volume are reduced just enough to carry the sand to the bottom of the hole. So, here you can see the densified the soil here in this region. So, in this slide now what we are seeing is the actual compaction taking place during intervals of around 0.3 meter lifts or so, and which are made in returning to the vibroflow to the surface. So, during this process what you can see is that this is a strata, and here this is that now the compacted zone with a thick soil deposit which is compacted with the desired relative density. So, here again the same process is repeated to compact this particular stretch also. The vibrator is first allowed to operate at the bottom of the crater until the desired density around the lower part of the machine is attained. So, by raising the vibrator step by step and simultaneously backfilling, the entire depth is compacted. So, in this process what we are doing is that what we have tried to explain is the sequential 4-step process, where a momentarily quick condition is created and the probe is vibrofloat is penetrated into made to penetrate into the ground, and the sand is supplied. So, with that by switching on to the flow to the top jets and allowing the water to flow, with that we are able to allow the sand flow to the bottom, and by creating this condition sequential by returning at the rate of around 0.3 meter per minute, repeating the same steps, we will be able to achieve the compaction at the deeper depths. So, the next method of compaction we have listed is by around blasting or by explosives. So, this is also a method which is used widely. So, the range of soil grain sizes suitable for compacting by blasting method is same as for vibroflotation. So, we have seen the range of soil grain sizes suitable for blasting method is same as for the vibroflotation. In this method, the compaction is achieved by successive detonations of small explosive charges in saturated soils. So, in this method the compaction is achieved by successive detonations of small explosive charges in saturated soils. relative densities of 70 to 80% up to a depth of 20 to 25 meter can be achieved. So, relative densities up to 70 to 80% can be achieved by this method, the compaction by explosives, and up to a depth of around 20 to 25 meter can be achieved. So, this is a process in which the energy is created by detonating a dynamite which is having a peculiar chemical composition. With that, we will be able to achieve around 70 to 80% relative density up to a depth of around 20 to 25 meter. And the soils, range of soil grain sizes which are suitable for this method are same as the one for vibroflotation. So, predominantly for sandy and gravelly soils this is used. And explosive charges are 60% dynamite, 30% special gelatin dynamite and ammonite are the most commonly used, are placed about the 2/3 times the thickness of the stratum to be densified. So, here at the 2/3 times of the stratum thickness, suppose if the H is the thickness, at 2/3 of the stratum thickness this explosive charge is placed. So, the spacings of the chargings vary from 3 to 8 meters. The spacing of the charges varies from 3 to 8 meters, and 3 to 5 successive detonations of several spaced charges usually required to achieve the desired compaction. So, a grid of these detonations have to be planned to achieve this degree of compaction. The shock waves which are created due to blasting cause momentarily liquefaction of the saturated sand, so followed by densification. So, the shock waves which actually create a momentarily create something called liquefaction and followed by densification, that is the concept. So, this method requires because of this practically no compaction is achieved in the top 1 meter of the layer. So, this top 1 meter of the layer is required to be usually needs to be recompaction by rollers. So, that is means both compaction by explosives and then this roller compaction has to be adopted. The shock waves due to blasting cause liquefaction and which is followed by densification. That is how the compaction process is done. So, the blasting by explosives, the influence radius if you wanted to calculate, so this can be defined as W is equal to CR cube, where W is the weight of the charge and C is the constant which is 0.0025 for 60% dynamite, and R is the sphere of influence, R is the sphere of influence. So, if blasting is used in dry or partially saturated soils, pre-flooding is desirable. So, because we said that, so a saturated sand deposit, a gravelly deposit, if it is undergoing blasting, so because of that it is possible. Suppose if a partially saturated soil deposit is required to be densified by this method, a pre-flooding of the site is required before detonating the this explosive charges. So, compaction by pounding or dynamic compaction or high energy impact used for improving surface and near surface zones of soil and fill material whose existing condition is considered to be marginal or inadequate foundation surface. This method consisting of dropping of a heavy weight, sometimes ranging from 2 tons to 15 tons at a height equivalent to around 10 meters to 30 meters. So, during the process the potential energy which is gained is transferred to the in the form of a compaction energy to the soil to densify the soils. So, at each point whenever this repeated heavy damping of loading is done, so a crater is formed, the soil will be displaced. So, with that process a grid of locations when we do in a particular site, we will be able to densify the soil in the particular area. So, this is basically used for improve the surface or near surface zones of soil and fill material whose existing condition is considered to be marginal or inadequate foundation support. That is one thing, is that the condition is marginal or inadequate for carrying the load which is going to be induced because of a forthcoming structure. Usually a closely spaced grid pattern is selected for the pounding locations and the multiple poundings are required at each drop location. Typically 5 to 10 drops are required. That means that the weights ranging from 2 to 10 tons and with drop heights ranging from 10 to 30 meters required to be at each particular location around 5 to 10 drops which are required to be carried out at a closed spacings, so that the entire area gets densified and the density can increase. So, this is can densify loose cohesionless soils, fracture and densify the buried building rubble or building debris such as that which exists at the old building sites, consolidate the fine grained soils and compact buried garbage bills, or this is widely used in compacting the municipal solid waste sites. that is in the landfill sites, this dynamic compaction method is widely used. So, can densify the loose cohesionless soil and fracture and densify the building rubble or a building debris at old construction, old building sites, and consolidate the fine grained soils, sometimes something called a dynamic consolidation, a dynamic compaction process, and compact the buried garbage or garbage fills or municipal solid waste fills. So, the pounding creates a depression at each drop location and also produce an aerial settlement. As you can see in this slide, you can see these are the different craters which are created because of the dropping the weight from a certain height, a certain weight from a certain height. So, here you can see the rig is shown at a particular site where the weight is hanged here and then is about to release here. Here in this particular portion here, the weight which has been released onto the soil can be seen here. So, in the process now, when this set of craters and set of craters have been created in this particular area, this actually creates a sort of depressions, and so this entire area will now tend to become compacted. So, we have tried to see different methods of in situ densification of soils, and we have tried to see some methods for compacting soils in the laboratory, both standard Proctor compaction and modified Proctor compaction. Then we have discussed about the field compaction specifications, method specifications and product specifications. Then we have seen some illustrations in problems in 1.1 and 1.2, where we try to some problems pertinent to compaction. Then we also have discussed the various factors affecting the compaction process and how the role of water is important in the process of compaction, and we brought out the relevance. Finally, let us look the compaction generally leads to the following desirable effects in the field. Like our aim is to produce the soil deposit with increased shear strength, so that we are able to support the structures with higher loads. This means that the larger loads can be applied to compact soils since they are typically stronger, and reduced compressibility. This also means that the larger loads can be applied to compacted soils since they will produce smaller settlements, and reduced permeability. This enables the soil's ability to absorb water and therefore reduce the tendency to expand, shrink and potential for the liquefaction. So, the compaction process produces increased shear strength, reduced compressibility and reduced permeability. So, improves the performance of the soil deposit in supporting the or in deriving the functions for the particular structure. So, this class we try to complete and cover the most of the salient aspects of the compaction. So, this with this lecture we are able to complete the compaction of soils.